Testing, 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 testing. Let's start our lecture. So how you guys doing? Good. So this is our fifth lecture, and today we will talk about the pointers, stacks, finite state machines. Uh, so for this lecture, you want to read through the ebook chapter 4. You will find more details about our lecture contents. Here's our agenda for today's lecture, and our first midterm will be on Monday, October 13th, from 9 to 11:50 during our lab section. And I checked our calendar. It's a Columbus Day, but I think it's not a holiday for CSU Monterey Bay, so we should be able to have the midterm on that day. It will be in this room, Pacific Hall 105, and it will be on paper. I will print the midterm questions for you, and I recommend you to use a dark pencil, and say you will have some coding tasks or questions. So by using a pencil, you can modify, easily erase your solution and modify it. So that's some personal suggestion. Of course, you can use some other pen you like. Okay, doesn't matter. So it's closed book and no calculator, and I will print out the commands. You're also welcome to print out the assembly language commands. I remember I shared with you a file in the canvas. You can print that. So any questions for the exam or no? Good. And you want to, the deadline for your lab 3 is Sunday at midnight. So you want to submit your lab 3 before Monday. And because in our Monday's lab section, we will go through all our previous labs from lab 1 to lab 3. We will discuss the solutions, and I will share with you how to, when we face a question like that, how do we, maybe you understand the logic, but there might be some coding issues. We will go through the logic, and I'll write the coding part for you, and so we can discuss how should we start a problem, how do we define the problem, and how do we modify the code while we are coding. Okay? So for today's lecture topics, we will talk about the pointers, the stack, and the finite state machines and structures, and we will go through a few questions, some examples. So first, is the operator, okay? A pointer. So pointer is a variable that points to the memory address of another variable, so which is commonly used in C programming. And the star operator will help us define a pointer. So there are two ways to write a pointer. You can write, say, for example, so you can write unsigned integer 16 underscore type, and then a space, and star PT. PT means pointer. And you can also, doesn't matter where the star is, okay? You can also put the star after this, the data type. So, and then space, and then letter P or PT, which means the pointer. So either way is fine, okay? It's just the two ways to define the pointer. actually, I think there's no difference between them. And like I mentioned, the pointer points to the memory address of another variable. For example, if this is our memory, say for example, this is our address, x 0, 0. And let's say if this is our variable x and its value equals 5. And after we define a pointer, if say you write something like star p, use pt. This is our pointer's variable, and use the and symbol x. So x is our variable, and symbol will fetch the memory address of the variable x, and will save it into a pointer variable. So this will be our, so the pt's value, this is pt, the value will just be x 0, 0. It will save the memory address of the variable x. And if you want to assign the value, say 5 to another variable y, say for example like this, and if we put the star, single star before the pointer, this will call the difference, dereference. This will fetch the value saved at this memory address, which is exactly 5. And in this case, y will equals to the value of this x. So y will equals 5. Okay, that's what dereference means. You know? So clear? And if we, for the binary operator, you know, y time is just the multiplication. So it's x equals y times z, and x star equal 2, which just means x equals x times 2. Okay. So the second is the AND operator, and like I mentioned, if we use the pointer variable equals the AND variable name, and this will save the memory address of the variable into the pointer variable. Okay. And for the binary AND operator, it just performs the 32-bit wise logic ANDs. And if we use two AND symbols, it's just the operator to perform the Boolean AND. So that's some difference between them. So next is the pointers. There is a quick example. Like I mentioned, the pointer is the address used to refer to a variable. And this is how we can define its unsigned integer 16-bit. We have two variables, the var and x. And we also declared our pointer, which is the star pt. And in the main function, we save the memory address of the var into the pointer variable, and to do the dereference, we just use the star pt, and this will give us dereference our pointer to the value which is 1000. I think this is assumed that our var has a value of 1000. And we can assign the value to another variable. Say here, with x equals star pt. This will assign the value 1000 to the variable x. And to write, when we want to increment the value of the star pt, you want to put the parentheses in this way, because the logic is clear. And if you use the following line, it's a bad example, because this can be very confusing sometimes. And the benefits that we use the pointer is that it can realize the dynamic memory allocation, so we don't have to copy large data structures. If you just use the assign the variables directly, sometimes we have to copy a large data structures into a new location and then do the data manipulation, which is more either time consuming or requires lots of storage and kind of decrease the efficiency of the data manipulation. So that's why we want to use the pointer to manipulate the data in the memory directly. So here's another example for using the arrays. And similarly, you can define the 200 as a context, which is size, which is 200. And this is how we define or declare the pointer variable, which is dpt3. And this is how we define the array called data3, and which has 200 elements in the data3 array. And inside the debug3 init function, and you can see that we have a dpt3 equals data3. So is this correct? So this is a quick question. Does this look right?
No, because don't you need the brackets after data3?
That's a good point, but actually this is correct. Because data3 is an array, so if you write data3 like this way, because remember when we access to the array, we have a dpt3 equals the data3. But data3 is an array. So in the same programming and for our embedded systems, so this is equivalent to and data3 0. So because if we don't give it an element, by default, the C programming will assume that the pointer will point to the first address of the array. So if this, for example, if this is our array, data3, and the pointer dpt3 will point to this memory address directly. Makes sense? Because that's the first element. But only array can do this. If you change the stack, and it's not, this is not the right syntax. But for array, it's okay. Okay. So let's go to the next one. And at the bottom is just straightforward. This is the reference. And what this does is that capture a value. So we have we can assume this letter D is an input. And this means that we save the value of D into the first address of the memory. So cause this is D reference, and this will go to this point, and the D will saved in the first location. Okay, makes sense. And dp3 is plus plus, and this is address, and then it will go to the next address for this. Okay, here's another example for the stack. And similarly, we can define the pointer like this and the stack size. And you see that for the stack, we have to use this standard syntax. We cannot just use our stack name directly. And this is a push function. And so we have a letter D. And because for push, we have to minus the address first and then save the D into our stack. And so here's another one for the pop. And remember for the pop, we pick a value from the stack. And in this case, we have to define or initialize the letter D inside the function. and then we can just assign this value to the letter D, and then add our address, and then return the D. So this is how we pop an element from the stack. So any questions?
Can you go to the last slide for that?
Okay, sure. Okay. So the difference between the push and pop is that for push, we decrement the address first and then push the value into the stack. For the pop, we pop the value first and then increase the address for the stack. So that's their difference. Good. Okay, next I'd like to introduce a concept in the embedded system, which is called the abstraction. So software abstraction allows us to define a complex problem with a set of basic abstract principles. So you can define a problem with a minimal set of basic abstract principles, concepts, and you can separate concerns while the interface, the policy mechanism. So it's a, a straightforward method. It has three advantages and faster to develop and easier to debug because we separate a complex problem into small pieces of problems. And it also is easier to debug because for each section, it will be a simple task for a complex systems. And you can, it's also easier to change, and you want to change if you want to modify a problem or do some debug, and it's easier to change a small section rather than a complex system. So that's the benefit of the abstraction. And in the next slide, we will discuss the finite state machines, which is kind of a classical example for the finite state machines. Okay. So let's go. Okay, let's go to the next. So the finite state machines, or FSM. So the first question is, what is a finite state machine, right? FSM is kind of an abstraction that describes the solution to a problem, very much like an algorithm. But for algorithm, we have followed fixed steps, to solve the problems. But for the finite state machines, we can describe the system as a machine that changes state in reaction to the inputs and produces the output. And let's go through some concepts for the finite state machines. So I mentioned for finite state machines, that's the system that can have inputs, can have multiple inputs, and we can also have multiple outputs for system. So we have system logic inside this one. And for finite state machines, we will have 5 things. Can you guess what we did for the finite state machines? Look at this graph. What should we have for the finite state machine? timer inputs. Yeah. So first we have set of inputs. Our second outputs. Yeah, great. We have set of outputs. And what else? Logic, to be more specific, like some logic is very abstract, right? It's very
Logic things.
actually it's called you can call it the states. You know, it's the kind of what our states are, what in our system logic. We have set of states. What else? We have input output, we have states, if we have multiple states, our finite state machine will change between the states, right? So we have state transitions. And usually for state transitions, we have two types of transitions. One is by using graph, it's called the state transition graph, or we can use tables called the state transition table. And another way we can describe the state transitions is by using a matrix. Okay? In this class, we don't cover matrix. We mainly focus on the state transition graph or state transition table. Thing is, we have the state transitions. We can change from different states, and we have inputs, we have outputs. But how do we define our outputs, right? How do we determine what we should output based on our states or based on our inputs? So we also need output determination for our output. So that's the 5 things for our finite state machines. And usually we have 2 types of state machines. One is called more finite state machines, more FSM. So for the more FSM, say for example, we have a next state, which will be a function of our current state and our input. And we also have output. For more of FSM, it means that our output only depends on our current state. This will be our current state. And we also have another type called mini-finite state machines. Mini-finite state. And for the mini-finite state machines, the next statement is the same as this function. So next statement will be the same, like the f function. So I'm not write it again. But for the output, of the mini state machines, it also depends on. So besides the current state, it also depends on input. So they have the same next statement, but for the output, they're different. This is for the more finite state machines. This is for the mini finite state machines. And you can see that the mini FSM is more complex than the more FSM, But actually, most of the mini FSM can be expressed by using the more FSM. So this is a more fundamental one. And in our lecture, we will focus mainly on the more FSM. Let me show you one example what this means for the finite state machines. Let's say we want to work on an example. We want to have a system that we want to recognize if we have number of if we have odd number of ones, the system won't have all we have all the number of ones. Okay? Still we have a system and we have our input sequence. And our input sequence might be 1, 2, 0, 1, 2, 0, 1, 1, 0, or something. And the bit will comes into the input 1 bit every time. Okay? We also have our output. So the output will count if we have all the number of ones, and say if for our first bit, when it comes into our system, we have one right, which is odd number. So we will output 1. We have our first input, and since the second and the third bit are 0 comes into the input, so we still only have 1, 1. So in this case, we will keep output 1 for the first 3 bits. And in the fourth bit, we have another 1. So we have 2 1s. And now it's an even number. So our when we get an even number, we will output 0. Okay? So our next bit is 0. So also we will keep 0, 0, until we have another 1. Now we have 3 1s, which is an odd number again. So then we will output 1 again. So make sense? Any question for this example? Because it's very important to make sure you understand what we are realizing here for this small system. So we just recognize the odd number of ones. Okay. So in this case, how do we define this? How do we use FSM to define this? Okay. What's our input? First, we need the input, right? So what's our input? What's our input? 0 and 1s, right? Good. So first, we need to define our input, which are just 0 and 1s. And second, we need to define our output. It's just 1 bit at a time. 0 and 1s, 1 bit. So what's our output? Also 0 and 1s, right? Yeah, because if we have an odd number, we will output 1. If we have an even number of 1s, we will output 0. So our output is also 0 and 1s. It's also 1 bit. And third, which is our state. So what for our output, what states we have? So it's either 0 and 1, right? So our output is either a number 0 and 1. So in this case, our state is either we have an even number or we have an odd number. Okay, great. So we have all 3 elements, and fourth is our state transition. So our seems that our state transition, we just keep transitioning from either 0 and 1s, right? So in this case, we are going to use the state transition graph. So how many states we have? 2, right? Great. So to represent our states, we use just the circles to represent our states. 1 circle, and 2 circle. And for this one, gonna put even on the top. So we have even, or we have odd numbers. Seems that we will, and this is our, we have an initial. Because at the beginning we output a 0, 0 is an even number, so we will just initial our state to even, right? So in this case, if we got an even number, output 0, right? If we got an odd number, output 1, so we write our output here. So if it's even, we output 0, and if odd, we output 1. Okay. So we have input is either 0 and 1. If our input is 0, we stay at state 0, state even. Right? So in this case, if our input is 0, so this means our input is 0. We stay at the even. So when should we transition from even to odd? Any thought? We get ones, right? So when we get a 1, we will transition from even to odd. So when our input is 1, say here we got our input is 1. Now we have 1 ones. So that's why we output 1 here. So our initial state is even. So when we have an input that equal to 1, we will then transition to the odd statement state. So for example, if we are at the odd state, if our input is 0, what should we do? Should we stay at odd or should we go back to even? So we stay at the odd, right? Because our input is 0, which means we still have an odd number of ones. So we will stay at there. Input 0. So that means if our input is 1, we will go back to the even state, because if we have odd number of ones, now we have another 1. Now we have 2 ones. We have an even number of ones, so we should go back to the even state. So that's why we have to go back to the even state. So is the logic clear? Any questions? Okay, so last thing is just our output determination, and apparently this is the more FSM. So anyone knows why this is a more FSM, not a mini FSM? So what's the difference between more and mini? For the more, our output depends on the current state, right? For the mini, our output depends on the current and the input. Because if we are at the even state, we will output 0 directly. So it does not depend on the input. No matter what your input, for even we will always output 0. And similarly for the odd, we will always output 1 no matter what the statement is. That's why this is the more FSM. So for the output determination is that when we have even, we will output 0. When we have odd, we will output 1. So this is how we define FSM sample. Make sense? Any questions, concerns? Okay, so make sure you understand this example. Good. Okay, so let's continue our slides. So like we discussed on the whiteboard, for our finite state machine, we have input, output, the controller, the state graph, or state table, which is basically the similar things. And for each part, for the FSMs, we have the inputs, outputs, states, transitions, and we have the graph defines the input-output relationship. And like we discussed, for a state, it's just a description of the current conditions. And for the state graph is the connections between the states. And the controller is just the software that inputs, outputs, and changes state and access the state graph. Okay? And let's look at this comparison. And like we discussed, a state graph, a state transition graph, or STG, has nodes and edges, and you can use the circle. Think of the circle as a node, and the edges. The nodes will refer to the state of the FSM, and say that and here we have a state called fast. We have an output, and in your lab for real physical device, we also have a wait time, because this is important to leave the embedded system enough time to react to your input. So that's why we add a wait time. Sometimes it's like 30, could be nanosecond or millisecond, depends on our embedded system. So for the edges, and this means that go to the next state if our input is 1. Okay. And on this one is the milli-state FSM. Okay. We also have the name. We have a wait time, and you see the difference is that for the milli FSM, our output depends both on the current state and our input. And this means next if input is 1, and this means output 1, 2, 3 if input is 1 and the state is go. Okay, so that's their difference. All right, let's go to the next one. And so this is the another example for the FSM, and assume this is Moore's FSM. The output value depends only on the current state, and the input will affect the state transition, and the significance is being in a state. Okay, we have input is when to change the state. We have output. It's the definition of being in that state. And for this one, we will go through this example first, and say that we initial to the state 5, and we have an output. We have a wait time. The bottom number means wait time. Probably 100 milliseconds make more sense. We have we have 4 states, 4 inputs, and 0. If we have input 0 and 3, we will just stay in state 5. If we have input 1, we will go to the next state. If we have input 2, we will go to the state 9. And similarly for the state 6, if we have 0, 3, this means that we will stay in this state. If we have input 1, we will transition from state 6 to state 10. And if we have input 2, we will go back to the state 5. Okay? Similarly for the state 10 and the state 9. So which is exactly the sequence expressed in these slides. We perform the output corresponding to the current state. Sometimes we wait amount of time. It's optional, but usually for because we are in the real world, right? Sometimes we need to wait, set up a wait time, to give the embedded system enough time to react to our inputs. And then it's just based on our inputs, we change the states, and then we go back to the step 1 and repeat all the steps. Right? We will have a 15 minutes break, and after we come back, we will continue our discussion for the structures. Okay, let's continue our lecture. So in our first section, we discussed what FSM is, and we plot some graph. And the next question is how do we realize it in the with the software, right? We know the logic, we know how it works, but how should we write it in the C code, right? So before we move on, I'd like to briefly introduce the structures and the struct in the C programming. The structure will collect elements of different size or types into one object. So when you build a structure, you may have different data types like characters or integers, or long, short, and maybe you want to put them into one structure. And in this case, you need a data type called struct, which is the user-defined data type. Let me turn off this. See what will happen. So, say what is this struct? Have a FSM, and we want to realize the code, right? And there's FSM, which is the state transition graph, something like this. And we want to realize it with software. And a struct is struct is a data user-defined data type which will store the conflict information. And for example, for array, we have an array, we can only save the same data type, right? All of them has to be same data type. But for a struct, we can have multiple different data types. Let's look at one example. Assume we have, this is a very classic example. Assume we have a field and we have a player. Define some structures for this one. Okay? Let's say struct. We want to have some different attributes of this player, of this player. And we will have a struct. And inside of the struct, we want to add a few attributes. Say we want to know this location, the x position, this is our coordinates. Y, we want to know the x position and the y position, maybe some other attributes. So in this case, we want to define some the unsigned character x position or x position. And similarly, we have on y position. And since it's a player, maybe we have some score or points, and we can define another the unsigned maybe using a short. And if our score range from 0 to 100, we can use short type. Well, we can call it points or score. So that's better name. So here we define a struct which is called player, and inside of the player we have also different data types. And then in the same programming, we can use type define a struct this is what we want to define. We want to define the type is player, and this is our structure player, and we can give it a name called the P type. This is how we define a new type. Define a new data type. So to use this, so here is the type defined struct player. This is what we have, and we call it P type. And in this case, you can use the name P type directly from P type. Let's define a new object called player one. And if we have a new player, we can use this. And we use the dot operator to access to the attributes of the struct. And say we can use player one dot x position, and say let's say this might be, let's say this is 30, 40. Right? So we can define x position to 30, and we can have a player one dot y position equals 40, and since this is the initial state, and the points might be 0. This is how we can define 3 different types. And inside the memory for this player one and one, so we can have different types, and say this might be the x position information, which might be 1 byte in the memory, and similarly for the y position. Y position, and it's also 1 byte, and we may have the score or the points, and which might be 2 bytes. This is the struct of layer one. You can see we can have different types, and the length of the data can also be different. This can be 1 byte, this can be 2 bytes. So furthermore, if we have like a more object in our, let's define something like this. If there are more objects, we can further use this to define our new object in this. So let's say this is a video games, and these are some shapes, and all the shapes abstract. Now we have 5, and we have 4 shapes in our display. You can call it shapes 4, and you can use the same type called the P type, and just call it shapes 4. And in this way, you can initialize the shapes object, and to access to the abstract, you can use the similar things. Like say if you want to access to shapes 0, you can use dot x position, and similarly dot y position, something like that. So this is a struct. And so let's go back to our example first section. Okay. Like I mentioned, we have a finite state machine. We want to use the code to realize these functions, and we need to apply this struct data type or user-defined data type to realize this. Okay. So how we can do this. This is our question. Oh, by the way, any question for this? So let's say we still have our graph here, and this is our system to recognize the odd number of points. And we have the STG, and now we want to use the code, and we want to use the struct to build a structure. say we have struct, let's call it state. What should we have in our state? Any thoughts?
Variables for input output.
Yeah, that's good. Output. We have output. Let's say we have our unassigned, our character, just call it. And we have for our state, we have output 0, 1s. For our output, what else we have? That's not in the graph that we mentioned in the slides. For the output for the real physical devices, we need to have some read times, right? Because we need to have some reaction times. Should be this number, so this should be long or short different time. This is long and wait time for the because we have wait time, because for each time we need to leave some time for the input our data and to give the system enough time to process the data. So actually the wait time can be at here. This is the wait time. And what else we have in this graph for the state? Only the state. We have even, and then our next state is odd. When we are at odd, our next state can be even. So we need a next state variable, right, to save our next state. And that's why we have another on the character next. So for our next, we have two elements. Which is the index of state. We use 0 to represent the index, and say for the next, inside the next we will have two elements. So we use 0 and 1. We use the index to represent the state, and say at the 0, our next statement will get filled here. If our state is 1 or index 1, our next state will fill here. So makes sense. So that's why we have next 2 this one. And now let's write down this logic. As mentioned, first with the initial noise declaration, we will define use a word given at 0, and we define all as 1. So this is our start state, and we should use, if you want to user defined, should use something like this one, right? So just type so those are the keywords in the C programming, and we have a structure state, and we will give it a name called S type, which means state type. Okay? So those are the keywords. It's type defines keyword, structure state, which is predefined as like this one, and our name is the S type. Okay? So in our S type, we have a finite state chain which has 2 elements. We will have 2 because we have two states here, so that's why I have two in this finite state constraint 2. So this one will be for state even, and this will be for state odd. Okay, for each one, remember S type have 3 attributes: output, weight, next. So for the output, if we have statement even, our output is 0, right? So that's why our first element will be 0, and for the odd, our output is 1. And we also need to have some wait time. So the second element here, let's say we waited 100 milliseconds for both of them. So in this case, I have to write 100 here to call them. So this means we will wait 100 milliseconds output. Okay, so the tricky part is at here, and because for the next, we should have 2 elements for each one. So when we are at the state even, we use, remember, this is the next statement is a 2 element, and we use the index as the statement. Okay? So this means we are at, say for example, the first index is 0. This means that our input is 0. In this case, our next statement we will stay at the even, right? So in this case, this will be even. Okay. We'll stay here. And so the second element is index 1, which means our input is 1. In this case, we will transfer from even to odd. So in this case, this number should be odd. And in this one, we are at the state odd. When we are at state 0, index 0 means the input is 0. So we will stay at odd. So this will mean odd. And when we have index 1, it means our input is 1. We will go back to the even statement. So that's why the next statement is even. Clear? Any questions? All confusing part? Okay, so basically this is how we define using the C code and one us is here. So let's see how it looks like in the memory. Okay, so we have our FSF, FSN 0, FOS, FSN 1. So in some 0, we have 4 elements, which is 0, which is our output, And we have 100, this is the wait time. We have even output, we have even state, we have output. If even means 0, out means 1. This is the dot next 0 for this part. And this is the dot next 1. Similarly, for the state odd, we also have 0, 100 wait time, and we have odd, we have even, this one, 0. So this is the dot next 0. We will say odd, and this is the dot next 1. Okay, for the this is how it looks like in the memory. And you see we have different data types, and that's how we go. Any questions? yeah, I'll give you a few seconds to go through this quickly. Make sure you clearly understand the logic here and define a struct, and then we use the struct to represent our finite state machine. So that's why I introduced the struct first, and then explain how we can apply the struct to represent our FSM. So that's about the structs, and here's the example we talked about, and it's a little bit, the name is a little bit different, but basically it's the same thing that we have a struct, we give it a user-defined name, player, and we have two types, s and integer 8 for the x position and y position, and then we have maybe a life force, a third element. And then we use the type define to struct a player, and we give it another name, might be a player underscore. Crazy motorcycle. So we can rename it to some other names like sprite, because later on, if we have enough time, for your last live, it will be design a video game, which is exactly a sprite video game. And in the main function, you have sprite.x. Like I mentioned, you can use dot to access to the attributes inside the struct. And so you can define 10, 20, and life forms. And you can say inside the memory, it will be saved like this. And it can have different data types and also the different learns. So that's the difference between the structure and the some other data types like array. So we talked about the state transition graph, and this is an example in our previous slide. And STG, like I mentioned, STG is graph state transition graph. STG is a state transition table. Basically, it's the same thing. Okay? So for the table, it's basically that we have our first column is our state, and we have 4 different states. And the output for each statement, oh, this is the binary number 5, and this is binary number 6, and this is 10, and this is 9. Okay? This is the binary output, and this is the integer output, so it's the same thing. Okay? This is the wait time, and those are the conditions. You see that here we're also using the index as our to represent our input. So we have 4 different inputs. So that's why it's from index 0 to index 3. And so if we are at index 0, we will stay at 5. So this is what we did at here. So we stay at S5. And similarly, if we have input index 3, we will also stay at 5. So if we have index 1, we will go to the state 6, and that's why we have state 6 here. And if we have index 2, we will go to the state 9. So that's why the next state is here. So this part is exactly the similar things called the next statement. If you look at our whiteboard, we have some similar things, right? We have the next state, but in our example, we only have 2 elements, like this one. So that's why the next array we have all or even based on the index. The index represents our input. So yeah, so here's basically the same thing. This is the state transition table. And we have state, we have character name, which is the 4-element array. We have output, we have out, we have wait, we have next. And this is how we initialize our state type. And, oh, here is the added the cost. Remember that cost means the constant, which means once we define it, we can no longer change the content of this structure type, and it's renamed as st_t, and inside it, it has FSM4. So if we go to the next slide, so basically it's the same thing, and so it's defined as 5, 0, index 1, index 2, index 3. Let's look at similar thing. So let's look at only one row. So this means we are at, this is our name. Remember, if we go back, we have our first attribute is the name. So that's why we have a name, which is the current state. And the next is the output, is 5. We output 5, so that's why this is 5. And this is our weight. And we have the index from 0 to 3. So that's why when we are at index 0, we stay at as state 5. When we are at index 1, we transfer to the state 6. So that's why we have S6. And then this is S9 and S5. So this is how we define it in the C programming. And next. Okay. This might look complex. I'm gonna give you like 5 minutes to go through this example and make sure you understand what this means, and then we can discuss this together. And I was actually trying to ask you to think about this, but since I already show everything, but it's okay, just take a few. So this is how the Mustang, the light works. If you look at this video, so the first, on the inside part, the first light will be on, and then go to the next one. And this is the left LED, and this L2 is this one. L1 is the middle one. L0 is the outside light, right? And similarly for the right side, so R0 is this one. R1 is the second one. And R3 is the outside light. So I'll give you 5 minutes and go through how the FSM looks like. Okay, let's look at one example together. Say let's start from the initial, because at initial all the lines will be off, so that's why we have it uses 6 bits to represent all the lines. So based on what the size, the bit 5 will change to so bit 5 is this one, so this is the 0 0 0 0 and 0 0 0. Okay, so bit 1 is bit 0 is this, bit 2, bit 1, bit 2, bit 3, bit 4, bit 5. Okay, that's all the lines. Okay, so let's take a look at turn right. Maybe let's look at turn right. What turn right will happen? So turn right means that the input is 0, 1. So which is, so if we don't do anything, it's 0, 0, we will, of course, we will stay at this state. And if it's 0, 1, on this side of the light will turn on. The bit 2 will turn on first, and then bit 1, and then bit 0. So if we go to the 0, 1, which means turn right, and we will go to the R0 state, okay? So the bit 2 will turn on first. And if we are still at turn right, and we will go to the R1, this statement, okay? So that's why the second light will be on. And then if we are still at turn right, we will go to the R2 state, which all the 3 lights will be on. So that's why all the 3 bits are on. And if we are still at turn right, and then we'll have a off, it will go to off, and then wait 500 milliseconds. If we're still turning right, then it will just keep going in this loop until we turn off it, or turn it to another, turn it to the left, it will jump to the other side, right? So, make sense? Logic is clear. Let's go to the okay, seems my computer is frozen. Let's wait a second, see what's happening. Yeah, I think it's frozen for some. Oh, oops. Yeah, I have one more slide to show you. Let me show this slide. So, okay, yeah, this is the last slide. And basically what I want to show you is that it's very similar things. We have the state name from R0, 1, 2, and left L0, 1, 2. And for the output, we are instead of using binary values, we are using the hexadecimal values to represent this value. And say, for example, this is like this R2 is for 7, and because this is bit 0, bit 1, bit 2, that's exactly 7, right? So that's why we have OX07 here. And time is just wait time. We have 3 inputs. It's either we do nothing, or we turn left or turn right. So that's why we have 0, 1, and 2. And the following is just how we switch between the states, okay? Any question for this? Okay, so that's all I have for today's lecture. I think we can end a little bit early today, but I want to mention our plan for next week. For next Monday, we will review our lab 1, lab 2, and lab 3. Basically, I'll have the coding and to show you what the logic is. I won't share you the code directly because you will see maybe 10 or 20 lines. So we want to go through the logic together and see when we face some challenge like this, where should we start? What types or what variables should we initialize at the beginning? And then we go through all the code. And I think we should have enough time to go through all the 3 labs. And if we end early, we will just end a little bit early on Monday. So you have more time. You can use the time to review the first 3 chapters. Our first midterm will only cover the first 3 chapters. So I think finite and state machine will not be included, so only the first 3 chapters. On Tuesday, for half of the section, I will introduce you the statistic interrupts. And for the other half section, we will review some key concepts from the first 3 chapters. Okay, that's our plan for next week. And our midterm will be then the following Monday for the midterm. Okay? Okay, see you. Bye. Take care.